Swayam Prabha. Digital India. Educated India.
Hello all. In this video we will be looking at engineering constants. Until now we have been looking engineering constants such as E1, E2, G12 and Poisson ratio nu12. But whenever we talk about these constants, these are in the material coordinates, which means when I say E1, the direction 1 is the principal direction, and similarly E2, the direction 2 is the principal direction. But it is not always the case that we are working with perfectly aligned laminates, but as we showed in the last 1 or 2 videos that we do consider these generally orthotropic materials, meaning these laminas are at an angle to the principal directions. Now, once we accept this, that we have an angle theta, how do we define these engineering constants? Though we can go ahead and use this E1, E2 and G12, but it would be nice to define some constants in terms of these body coordinates such as Ex, Ey, Gxy and nu xy, and we will see that these are just only a few of the constants, but we can have few more constants. The purpose is to give you an idea about what is the effective stiffness of the lamina in these body coordinates, like the effective stiffness in the x direction, the effective stiffness in the y direction, or the effective shear stiffness in this plane xy. So, let us see how we can show these engineering constants in the body coordinates. So, for this we will start by looking at the relation between the stress and strain in terms of the Compliance the transformed Compliance matrix. So, here are the 3 components of the strains and the 3 components of the stresses. Now, let us think of a scenario where there is only stresses in direction 1. So, meaning that here is your the infinitesimal element we are looking at, but this time it is at an orientation angle theta. But the loadings we are assuming here is that there is only a uniaxial load in the x direction and the rest all going to 0, meaning sigma x is non-zero, but while sigma y and tau xy are 0. In addition to the other 3 stress component, they are also going to 0. So, in this case, now let us see what is the strains we expect from this generally orthotropic material. So, looking at the strain stress relation, we should be able to write what is epsilon x. Similarly, we will also see that it will have a component epsilon y and gamma xy. But now let us try to introduce some engineering constants. So, for this loading condition, first let us start with the first engineering constant Ex, where we define Ex is the stiffness along the x direction, which is given by stress by strain. What is the stress we have acted? The applied stress is sigma x and the strain in that direction is epsilon x. But from this strain stress relation, we should be able to write what is epsilon x. Epsilon x is S11 dash times sigma x, since sigma y is going to 0 and tau xy also goes to 0. Okay. Once I cancel out this sigma x which is there both in numerator and denominator, what we are left out is 1 by S11. Okay. But from this loading scenario, is there any other strains we get? The answer is yes, we also get the strain epsilon y. But what does epsilon y represent? It represents the Poisson effect, meaning if you are loading in one direction, what is the change of strains in the transverse directions. So, let us say we are writing about Poisson ratio xy. This is minus of the strain in the loading direction, which is epsilon x, and in the numerator we have epsilon y. Now let us see how we can write in terms of this transformed compliance matrix. So epsilon y is S12 times sigma x, and epsilon x we have already written in the previous equation is S11 bar times sigma x. Here I could have written also as S21, but we have already know that this stiffness matrix and the compliance matrix are symmetric. So instead of writing S21 here, I simply wrote it as 12. Okay. Now if we remove this sigma x from numerator and denominator, we end up with this minus S12 by S1. Okay. But is there any other contribution we get because of these loads we have discussed? So we notice that we also find gamma xy or the shear strain gamma xy because of these loading sigma x. And what is gamma xy? Gamma xy is a shear strain. Shear strain coming from the applied stresses are normal. So previously if you recall, we said this S16 is a coupling between extension and shear. So when we see this gamma xy, we are able to see a extension shear coupling. To define that, we introduce a new coefficient called as the coefficient of mutual influence. Uh, Shown as x comma xy, which is the ratio of gamma xy, the shear strain by the corresponding normal strain epsilon x. So how can we write the shear strain gamma xy in terms of these compliance matrix? We can write it as S16 times sigma x, and say epsilon x we already know is S11 bar times sigma x. So which should give you the ratio as S16 bar by S11 bar. So essentially what we are trying to show with this new coefficient, the mutual influence coefficient, is how much is the shear strain with respect to the corresponding normal strain when we are applying a uniaxial load with all other stresses components going to 0. So here we are able to define 3 constants from the single experiment. What are those constants? Ex, Poisson ratio nu xy, and this new coefficient of mutual influence x comma xy. Okay. Similarly, I could have designed one more experiment where for the same infinitesimal element if we apply uniaxial stress in the direction y. From this I should be able to define one more engineering constant Ey. Essentially the stiffness of this lamina in transfers to this direction or in direction y, which I can write it as sigma y by epsilon y. We should be able to and here let me also reiterate saying that sigma y is the only non-zero stress and the other stresses like sigma x and tau xy go to 0. So in this case how can I write epsilon y using this strain stress relation? One should be able to write it as S22 bar times sigma y, which should give you as 1 by S22 bar. So from the second experiment I should be able to write this new elastic constant E y. Similarly, I could have designed one more experiment where we apply shear or pure shear without any normal stress. So we are again taking the same lamina with this angle theta and then apply these shear stresses tau xy. So, because of we applying this shear stress tau xy, first thing is we will notice shear strain, and how do we write this shear strain or how do we bring that relation? We write it in terms of an elastic constant Gxy, where we have the shear stress applied tau xy divided by the shear strain gamma xy. So, how can I write this gamma xy in terms of the compliance? We can write it as S66 bar times tau xy, which should give you this G xy as 1 by S66 with a bar. Okay. Is there any other coefficient we can get from this last experiment? The answer is yes. We can here again talk about this extension shear coupling, but this time because of applying the shear stresses, what are the normal strengths? How do we get that? Again we introduce one more coefficient of mutual influence, this time xy comma x, which we can define as epsilon x by gamma xy. How can we write this? Epsilon x will be S16 bar times tau xy, and gamma xy is S66 bar times tau xy, which should give it as ratio of S16 bar by S66 bar. So, from this last experiment we are able to find two more elastic constants, which we name it as Gxy and this coefficient of mutual influence written as xy comma x. So, let me box it. So, we can see what are the elastic constants we have discussed here. So, we have got 3 elastic constants Ex, nu xy and this coefficient of mutual influence x comma xy, and then from the second experiment we got this Ey, and from the third experiment we got this Gxy and another coefficient of mutual influence where we write it as xy comma x. Now that we have defined these engineering constants, let us look at few examples to get a physical feel about how these values vary with the orientation angle theta. So, for this we will start by looking at Ex and Ey, which are the stiffness in the directions x and y. So, here are the expressions for Ex and Ey written in terms of the elastic constants in the material coordinate system, which is E1, E2, G12 and the Poisson ratio and the orientation angle theta. So, here C is the cos theta and S is the sin theta. So, as you can see we have written these Ex and Ey as a function of E1, E2, G12, Poisson ratio G nu12 and the orientation angle theta. So, now let us take an example of glass epoxy, where we take these E1 and E2 values. As you notice that the E1 value is much higher compared to E2, because we are now discussing about one being the direction of the fiber. Along the direction of the fiber we said the stiffness is high, and these are the Poisson and the shear modulus. So, for this here it shows how Ex and Ey vary with the angle theta. So, when we say it is 0 angle, what we mean is the fibers are all aligned along this direction x, and when we are looking at angle theta being 90, we are saying that the fibers are all along the direction y. Okay. And similarly, of course, all the other angles are intermediate, like 30 being 30 with the x axis and 60 with the x axis is something like this. Oh. Now let us focus our attention to Ex, which is shown by this line. So, we see for orientation angle 0, the stiffness is the highest, but as we increase the orientation angle going from 0 to 90, it gradually decreases and finally it reaches its minimum value at 90 degrees. And if you again look back at these values, this is quite evident because we know the E1 value is maximum and E2 is the minimum. E1 is where we get when the orientation angle is 0 degrees, and E2 is what we get when the orientation is 90 degrees. Okay. Similarly, now if we pay our attention to the second curve Ey, where we are looking at stiffness in the direction y, we see it has the least at the angle 0. So, meaning let us say if we are focusing on this curve and we are applying the loads in the y direction or perpendicular to the fibers, we see the stiffness is the least. But as we increase the orientation angle from 0 to 90, this Ey value keeps increasing and then it reaches a maximum value at 90 degrees. Why is the stiffness maximum at 90 degrees? Because that is when we have all the fibers along the loading direction, because now we are loading in the direction y and the fibers are also in the direction y. That is the reason why we have the maximum Ea value at theta equals 90. So, one very important point for us to look here is, though we know that the properties are high at an angle of 0, most times these composites are prepared by manual, means using hands we try to align the fibers along the direction where we want maximum load. But there is always a chance for human error. Let us say instead of aligning at 0, there is an angle error of 10 degrees. So, which means at 10 degrees you already see there is a drastic reduction in the properties. And even if it is more than that, let us say 15 or 20, the changes in the properties are very significant. What it means is one should be very careful while preparing these composites. Any small change angle like 50 degrees, 5 degrees or even 10 degrees can vary your stiffness by maybe 10% or even 25%. For example, here when we are talking about 15-degree variation, there is a huge decrease in the modulus. So, this is one point one has to take home by looking at these plots of Ex and Ey. But now let us look at the other engineering constants. First we will look at the shear modulus Gxy. So, here is the expression again written in terms of E1, E2, G12, Poisson ratio nu12 and the orientation angle theta. So, S and C represent the sin theta and the cos theta. So, looking at here again we see when we are looking at 0 orientation and then you apply the shear stress, we have the least shear stiffness because here we have the minimum. Similarly, again we have the minimum at an orientation angle of 90 degrees, where we are orienting the fibers in the y direction and we apply the shear stress. But the interesting point here is we get the maximum at 45 degrees. So, meaning like if we have the orientation angle at 45 degrees, the fibers are at 45 degrees to your x axis, and then when you apply the shear stress, then we get the maximum shear stiffness in the component. This is very important because let us say now we are in an application where you are applying a shear load. Then this tells you that what is the preferred orientation. The preferred orientation is 45 degrees because that is when the shear stiffness is high. Later when we discuss about the designing or the principles of design, there This is the important design principle we use. So, in applications where there are shear dominated loads, then we prefer to have more of these 45 angle plies. Okay. Now, let us move our attention to the last of the coefficients or the engineering constants, where we discuss about this coefficient of mutual influence. Let me erase this. So, here we first notice that this coefficient value is negative, meaning that if you are applying a uniaxial load and we expect this axial strains to be expanding, then the shear is in the negative direction. But the interesting point to note is it has these values of 0 at orientation angles of 0 degrees and 90 degrees. What does this mean? It means when the fibers are along the direction x, then and your applied force is sigma x, there is no shear, which we know because we have already seen for a specially orthotropic material that if you are applying the loads or the uniaxial stresses along the x direction, there is no shear component or the shear extension coupling is 0. The same happens at 90 degrees when we have the fibers in y direction. But intermediate where the angles are between 0 and 90, we notice that there is a shear contribution and this shear contribution is maximum at some intermediate value. This value can change from material to material, which we will see in the next slide. So, in this slide we are showing you 3 different composites, the glass composites with red, blue with composites, carbon composite and aramide with magenta color. So, for example, when we start with looking for Ex, Ex is the stiffness along the x direction. We have normalized it with E2, where E2 is the transverse stiffness in the direction 2. Okay. So, here we see this red color is glass, blue is carbon and aramide is magenta. The point we are trying to say is in all of these composites the maximum stiffness occurs at 0 degrees orientation and the minimum occurs at 90 degrees orientation. This is quite evident, which we have already seen in the previous slides, saying that of course you will get the maximum stiffness if you align the fibers along the loading direction and the least you get when the fibers are perpendicular to the loading direction. But depending on the composite we choose, the values vary. But when we start discussing about the shear stiffness, we see irrespective of the material, meaning the red here is the glass, blue carbon and magenta for aramide. For all these composites, where do we have the maximum shear stiffness? For all of these, we have the maximum shear corresponding to 45 degrees. See, irrespective of the composite chosen, if it is a unidirectional lamina, then we get the maximum stiffness at 45 degrees orientation. And when we move to this coefficient of mutual influence, again as we discussed previously, irrespective of the composite chosen, there is at 0 degree orientation and at 90 degree orientation, there is no extension shear coupling. But at intermediate values between the 0 and 90, that is when we get this coupling, meaning even if you are applying a normal load, we do see this shear strains. So, now let us summarize what we have discussed in this video. We started by defining some engineering constants in the body coordinates such as Ex, Ey, saying that these are the stiffnesses in the directions x and y, and similarly the shear stiffness Gxy, and we also introduced a Poisson ratio, we know nu xy, but in addition to this we introduced another coefficient called the coefficient of mutual influence, which we said we can write it as x comma xy, meaning that we have the loading in the x direction and then we are looking at shear strain gamma xy by the normal strain epsilon x. There is a different variant where we said there is a second coefficient of mutual influence where we have the loading in the xy direction, which is the shear stress, and we look at the ratio of normal strain by the shear strain gamma xy. So, we also showed you with a few composites like the glass fiber, carbon fiber and aramide fiber how these values change. For Ex we said it has the maximum value at 0 degrees and minimum value at 90 degrees. Of course, we did not look at y, but I am sure we can talk about y now, saying that when do we have the maximum value of Ey? Maximum value will be at 90-degree orientation and the minimum value will be at 0-degree orientation fibers. But more importantly, we have seen for the shear stiffness, the maximum occurs at an angle 45 degrees. And for this coefficient of mutual influence, we have showed that it is for angles of 0 degrees and 90 degrees. We showed that there is no extension shear coupling. But at intermediate values between 0 and 90, we do have the shear strain, and which means that we do have this extension shear coupling. This should give a brief idea about how we look about the engineering constants in the body coordinate system. Thank you.